Hello friends, welcome to another lecture of quantum mechanics. Here we're going to discuss about conditions for physical acceptability of wave functions. Okay, so before we start, please subscribe the channel, hit the thumbs up button, also share with your friends, inspire me to create new contents for you. And so now let's start. And before we start, these things, the conditions that must be satisfied by a wave function, to be accepted as a wave function. So you must know what is wave function, and you should also know the normalization conditions. So I have already made 2 lectures on wave function and normalization of wave functions. So please go through these 2 videos. The links are in the description box. And if you want to follow me on Insta, this is my Insta ID, Ozaloikajit 123. Okay, this is my Insta ID. So if you want to follow me, then you can follow me here. So now you see, so we know that these particles, when particles, moving particles, when you say moving particles, there is a wave associated with moving particles, which is called matter wave, right? Because particles, when you say particles, it is nothing but matter, right? When these particles are in motion, there must be a wave associated with this, because we can't see this wave physically, because when you talk about these particles like electrons and protons, these are very small and they are moving very fast, right? And when you talk about the large things, large objects that we can see in our practical lives, in our daily life, though they are in motion, we cannot see the wave associated with them, because the lambda, that is wavelength, associated with a moving particle, depends on mass. It is inversely proportional to mass. In case of macroscopic particle, that those particles, large particles that we can see in our daily life within naked eye, so we cannot see the wave. But when we study about the behavior of the particles like electrons and protons, so though these are particles, but when we study the behavior, then we can say see they behaves like waves. Okay, they waves like behaves. So I think you must have heard about the dual nature of matter. Okay, so they shows particle nature as well as wave nature. Okay, so what does this wave says? Actually, to explain this, we used to take the help of the wave function. So wave function, it is nothing but this is function of position and time, that gives the complete information, complete information about a particle, actually moving particle. Okay, now this is a mathematical term, okay, that explains about the position and other informations about the moving particle, that gives the information of the moving particle. Okay, so now you see, suppose this is psi x, the wave function. Let me consider the case of one dimension only. So if wave associated with a particle, if there is a wave which is associated with a particle, so then it must spread over a certain region. Okay, when we say particle, so we can say it exists at a point, but when you say wave, it must be it must spread over a certain region. Okay, so if it spread over a certain region, that means so there is a chance to get the particle at any point within this region. Okay, but the getting the particle, chance of the getting particle at different point within the region is different. Okay, probability of finding the particle at this point is different, and at this point is different. So here the probability is more than the probability of getting particle at this point, right? So if you see the wave, Okay, so now you see the probability is given by this integration from minus infinity to plus infinity psi x and conjugate of psi x. So it is a complex function. Okay, it is a complex function. So hope you know what is complex conjugate of you know what is the conjugate of a complex number. If a plus ib is a complex number, then its conjugate is a minus ib, right? Hope you know these things. So now you see, if you integrate it from minus infinity to plus infinity, if x is infinity, plus infinity and minus infinity. So if there is a particle exists, particle exists, then so it must be somewhere between this region, right? So if you integrate from minus infinity to plus infinity, then the probability must be equal to 1, because it exists. If the particle exists, the probability must be 1. But here you see, if the wave is the wave is spread over this region only, then you can find a particle within this region, and outside this you're gonna get 0. Probability is 0. But when you integrate it from minus infinity to plus infinity, because as this particle exists, so that must be 1, because we must get the particle within this whole region, right? So hope you have understood this. So now you see, so what are the properties of this function? Okay, what are the properties of this function? Now let me tell you one by one. Now you see, this function psi must be finite for all values of x, y, and z. It must be finite. Okay, so it cannot be infinite. It must be finite, right? Because you see, as the integration from a to b or something else, whatever be the region, doesn't matter. If you take psi and conjugate of psi, and if you integrate it from a certain point to another point, okay, so it may be a to b or minus infinity to plus infinity, whatever it is. So there must be a probability. Okay, this probability cannot be infinite. It cannot be it cannot be undefined. Okay, so that's why this must be also finite. So it will be finite when this psi will be finite at x, y, and z, right? So that is the region. And what is the next condition that must be satisfied? I will give you all the conditions. First, let me explain. And next condition is, it must be single valued. Okay, it must be single valued. Okay, for each value of x and y, right? It must be single valued, because at the same point you cannot have two different probabilities, right? So that's why it must be single valued. And next one, it must be continuous. So psi must be continuous. It must be continuous, right? Because you see, all the things that we need, like momentum, kinetic energy, those informations can be obtained from psi. Okay, so if it is not continuous, now you see, if you take the operator of momentum, okay, if you take the momentum operator that is given by, suppose this is the momentum operator. If you have watched my previous videos, then you must have got this about the momentum operators, right? Okay, so here you see, here partial derivative involves. So that's why this function will be differentiable when this is continuous. Okay, so that's why it must be continuous. Otherwise we cannot find the momentum, kinetic energy using this operator, right? So hope you have understood this. So now you see, next one, this psi must have vanished when x, y, z, whatever you think, this tends to minus and plus infinity, right? As I have already told you that if the wave spread over this region, then outside this region the probability of getting the particle is 0, right? So that's why it must be 0 when x tends to infinity, right? So hope you have understood this. And partial derivatives, I have already explained that partial derivative of this must be also finite. Otherwise we cannot find momentum, kinetic energy using the operators, because the kinetic energy operators, the momentum operators, they consist differential coefficient, right? And now let me give you the conditions in written. These are the conditions to be satisfied by the wave function, to accept it as a wave function, right? So hope you have understood, and thank you for watching. See you in the next video. If this video is helpful, please do share with your friends and inspire me to create new content for you. And thank you.